seems to have happened?
18-year-old female college student appears to have been poisoned.
We're going to have to take this to the lab and run tests to identify the substance. Here are the results from the lab.
Since you're new here, I'm going to show you how we identify substances such as this. Now, a witness did tip us off, and we know that the poison was a mixture, and the compounds in the mixture only contain carbon, hydrogen, and oxygen. There are 6 more experiments we can conduct to determine the rest of the information we need. Thin layer chromatography, absorbance spectroscopy, gas chromatography, infrared spectroscopy, mass spectrometry, and nuclear magnetic resonance. First, we use thin layer chromatography to determine how many substances are in the mixture. Compounds are separated on a thin layer of absorbent material such as silica gel on a glass plate. This is known as the stationary phase. The strength of the intermolecular forces, or IMFs,
Meaning the forces between molecules.
correct, which is the differentiating characteristic for this experiment, will affect how far the solution goes in the plate. If the solution is more attracted to the stationary phase, it will not move the plate as far. However, if the solution is more attracted to the mobile
The
phase,
solvent.
it will move farther up the plate. This will affect the retention factor, which is the ratio between the distance traveled of the substance and the distance the mobile phase traveled. The smaller the retention factor, the stronger the IMFs. If we knew what the possible compounds were in our poison, we could run those as well and compare our data to see what the substance is. However, we did not use this method of identification because gas chromatography tells us how many substances are in a solution more accurately, as well as some of the substances might not separate effectively using TS. Next, we put the sample through an absorbance spectrometer. Absorbance spectroscopy tells us how well the substance absorbs light in the visible spectrum at different concentrations. Plotting absorbance versus concentration on a graph, we can then find the molar absorptivity using the Beer-Lambert equation.
And once we have calculated the molar absorptivity value, then we can run it through a database and see whether the compounds match our data.
Right. However, since the liquid we collected at the crime scene was transparent, this procedure is not particularly useful as the substance absorbs light that is outside the visible spectrum. Following absorbance spec, we'll use GCMS to determine how many substances are in our solution, calculate the percent volume of each substance in the solution, and find the molar mass and the mass of fragment ions. In this experiment, a known volume of our solution is passed through a chromatography column, the stationary phase, pushed by an inert mobile phase. This is where the solution is separated. The time it takes for each substance in the solution to pass through this column is called the retention time, which is the differentiating characteristic.
So the retention time will differ between each substance in our solution based off the strength of the intermolecular forces of each substance with itself and the stationary phase.
Correct. After the substance is separated in the gas chromatograph, it is then moved to the mass spectrometer. In mass spectrometry, a sample of a substance is passed through an electron beam, ionizing the molecules and also breaking some up into smaller fragments. These molecules and fragments are then passed through an electromagnet, which deflects them to a degree based on their mass to charge ratio. This ratio is the differentiating characteristic used to identify compounds, as no two substances will have the same full mass spec. Also, the peak farthest to the right on the mass spec is the molar mass of that compound.
Okay, so it looks like we're dealing with two different compounds, one with a molar mass of 74 grams per mole and one with 150.
Right. However, our data from the chromatogram was messed up in the lab. Only one peak appeared, indicating the presence of only one substance, although we know there are two based on the mass spec. This error makes us unable to calculate the percent volume of our substances. Although if we did have correct data, we could calculate it by using the area under each peak. The first step of the calculation is to divide the area under the individual peaks by the total area of all the peaks and multiply by 100. Once you obtain this percent area of each peak, you calculate the volume of each substance by dividing the mass fraction of the peak by the density of the substance. Mass fraction is equal to the percent area in a 1 gram sample, which we can assume it is. Next, calculate the total volume by calculating the sum of the volume of both substances. Finally, divide the volume of each substance by the total volume, multiply by 100 to obtain the percent volume composition for both substances. Infrared spectroscopy determines the bonds present in a molecule using various wavelengths of infrared light the solution absorbs, which is our differentiating characteristic. Knowing what bonds are present in our substance are crucial to determine the structure of our molecule.
So the peak at about 3000 wave number represents a carbon bonded to hydrogen.
Correct. The peak between 1500 and 2000 wave number represents a carbon double bonded to oxygen. Between 1000 and 1500, a C single bonded to oxygen, and 500 to 1,000 wave number represents the C double bond of this carbon. We determined this based off an IR spectrum table that shows bonds present at different wave number or absorbance values.
So in conclusion, we know our solution has a carbon-hydrogen bond, carbon-oxygen single and double bonds, and carbon-to-carbon single and double bonds. Can we tell what bonds go to what substance since our solution is a mixture?
Sadly, we can't tell which substances has what bonds. However, it helps us with our search because we know what bonds cannot be present in our solution. For example, we know hydrogen bonded to oxygen can't be present in either of our compounds. Alright, so far we know that our poison is a mixture of two substances, one with a molar mass of 74 and the other with 150. We know that they only contain carbon, hydrogen, and oxygen, and we know what bonds are present in our mixture. Now, the last test, NMR, will help us find the final structures of our compounds. The differentiating characteristic used in NMR is the number and location of hydrogen atoms in each compound. The spectrum given by NMR reports how many different chemical environments hydrogen atoms exist in each compound and the ratio between the number of hydrogens in each environment.
So all of that must be shown by the integration, splitting, and chemical shifts of those peaks, right?
Correct.
So now that we've analyzed all of our data, we can start to piece it together and identify our two substances. Through basic guess and check, we found two possible molecular formulas for our substances that only contain carbon, hydrogen, and oxygen, match the required molar masses, and have isomers that only contain bonds we detected in our FTIR experiment. These substances are C4H10O and C9H10O2. However, this does not tell us the exact structure of our molecules. For C4H10O, there are 3 possible isomers, and for C9H10O2, there are 4. In order to narrow these down, we first ran the C9H10O2 isomers through the ChemDraw software and predicted their NMRs. Only one of the isomers matched peaks that were found on our NMR, which is benzyl acetate. To verify this, we can integrate the peaks that match the ChemDraw by using the multiplet analysis tool to find the ratio of hydrogens. In doing so, we find that we get a ratio of 5 to 2 to 3, which perfectly matches the structure for benzyl acetate. From this, we can be sure that the 3 peaks on the right of our NMR were chemical shifts in one of the isomers for C4H10O. And after putting those 3 isomers through ChemDraw, only one came close to predicting an NMR that matches the 3 peaks to the right of our NMR, which is 2-methoxypropane.
So we can conclude that benzyl acetate and 2-methoxypropane must be in the compounds that made the poison that killed that girl.
Right, and it just so happens that these 2 compounds can only be found at the place where the victim's neighbor works.
Mr. Brown, I want to search this office. You're under the arrest for the murder of Lindsay Draft.